Hi, this is Tim. Welcome to the Math League YouTube channel. Today we're going to be taking a look at target round number 8 from test number 12107. That was the high school state championship in 2021. So what have we got? An infinite series that involves cosines. Okay, seems like I did a YouTube video kind of like this a few months ago, and I'm going to use the same sort of technique here today. For those of you who have read the solution that came with the test, I'm going to be taking a completely different approach here. All right, so the first thing I'm going to do is I'm going to go ahead and rewrite this problem. We're interested in f of 2020. Okay, so I'm rewriting it in sigma notation because it's just more efficient to do it that way, right? So we are, if you know how to put things in sigma notation, great. Basically what we're doing is we're adding a bunch of cosine of somethings over into the somethings, in this case is 2020. So if I start off with an index of 0, then basically I'm going to take 2020 to the first power. That's my first denominator, 2020 to the second power, and so on. So my denominators are always 2020 to the k plus 1. My numerators are always going to be cosine of some multiple of pi over 3. I start with 0 times pi over 3, 1 times pi over 3, 2 times pi over 3. So it's always k times pi over 3, starting from k and going on up to infinity. All right, so that's what this thing actually is in sigma notation. Okay, so I'm going to leverage a fact that I know about cosines, sines, and complex numbers that I'd like to encourage you all to know as well. And that is that if I have cosine of theta plus I sine of theta, we can also rewrite that in shorthand as cis theta. That means cosine theta plus I sine theta. That is equal to e to the I theta. Now, this is going to be helpful because what we're doing here is we're adding a bunch of cosines where the argument of the cosine is being multiplied by something. It'd be a lot nicer if I can put that multiplication inside the exponent of e, because that way it'll make it easier to deal with a geometric series. Now, the only problem is if I turn this into e to the I theta on the top here, I'm going to end up with a cosine part and an I sine part. I don't want the I sine part. So all we have to do then is say, okay, well, let's just go for the real part of this thing. So when we're done with the entire sum, my final step is going to be to take the real part of this and ignore the imaginary part. What that does is it gives me the answer that I wanted relative to the cosines and leaves off the stuff that involves sines. Okay, so I have this sum, and again, the reason that I wanted to put this in an exponent is because this now is a geometric series, right? So in particular, I have my first term. I can plug in k equals 0 to get my first term. That gives me e to the 0, okay? And on the bottom, I get 2020 to the 0 plus 1, or 2020 to the 1. So a is going to be 1, that's e to the 0, over 2020. Okay, now what's my ratio between terms? Well, every time k increases by 1, I am now going to be multiplying the numerator by e to the I pi over 3, right, to get an extra 1 in there. That's what this k does. And I'm also going to be multiplying the denominator by 2020. So my ratio is going to be e to the I pi over 3 over 2020. Now, that's going to be equal to cis of pi over 3 over 2020 by this formula up here. This is called de Moivre's formula, by the way, or de Moivre's theorem. Make sure you are aware of that because this is very helpful, as you'll see here in problems such as this. Okay, so we've got that as cis pi over 3. Now, cis, of course, is cosine of theta plus I sine of theta. So I can rewrite this as the cosine of pi over 3, which is 1/2, plus I times the sine of pi over 3, which is I times root 3 over 2. And that gives us a numerical value for our ratio. Okay, take what you know about geometric series. You know that for the sum of a geometric series is going to be a over 1 minus r. So all we have to do is plug in the stuff, okay? We plug in the 1 over 2020. I've got a 1 minus, and all this stuff down here is what I wrote for r. Let's simplify it a little bit. I see fractions within fractions, so we can do a little bit of simplification. The first thing we can do is multiply the top and bottom by 2020, and it's going to start to look like this. I still have fractions inside of fractions, so I guess the first one was fractions within fractions within fractions. I still have fractions within fractions, so let me multiply the top and the bottom by 2, and it's going to look like this. Notice the 4,039 came from multiplying this by 2. That's 4,040 minus a half times 2, which is 1. 4,040 minus 1 does give you 4,039. Okay, that's our sum. That's the sum that we have up here, at least. But I need the real part of it, right? So I need the real part of this thing in order to get my answer. And then, of course, I'm still looking for the numerator. Anyway, you want to get the real part of this, what we need to do is turn it into an actual complex number, right? Some real number plus I times another real number. Because we have an imaginary number in the denominator, we're going to have to rationalize it, which means I'm going to multiply the top and the bottom, not by the denominator, but by the conjugate of the denominator. That's where I replace the minus with a plus, and that instead of 4,039 minus root 3i, it becomes 4,039 plus root 3i. I multiply the top and the bottom by the same thing, right? So my final result is still the same number. It's just going to look a little bit different because now I can do some more algebraic manipulation on this thing. Let's go ahead and do that. If I take the top, I've got 2 times 4,039 plus 2 times root 3i. And then the bottom, you'll notice that this is basically of the form a minus b times a plus b, which is a squared minus b squared. So I got 4,039 squared minus root 3i squared. If I take root 3i and I square it, I'm going to get a negative 3, and I'm subtracting a negative 3, so that gives me a plus 3. Okay, so this is a better form for us to deal with. Again, this is the sum that we had up here, but in order to get the actual f of 2020, I'm going to need to take the real part of this sum in order to get this sum. All right, so we want to take the real part of this, and the real part basically means I'm just going to get rid of the imaginary part, so this goes away, and all that's left is the 2 times 4,039 on the top, 4,039 squared plus 3 on the bottom. This is f of 2020. Oh, wait, we're not done, right? Because we still need to figure out what the numerator is when this is written as a fraction. Don't just look at the 2 times 4,039 and be like, oh, that's my answer. What is that, 8,078? Don't put 8,078 because this thing will simplify. First thing you want to notice is that the bottom is the square of an odd number, in other words, an odd number, plus another odd number. It's even. The bottom is even, which means I can factor a 2 out of the bottom and the top. Okay, so we've simplified the numerator to 4,039 now, right? This 2 is going to cancel with the bottom. The question now is, will anything else cancel? All right, so this is where a little number theory comes in handy. What we're going to see is that I would need a number. If I'm going to cancel something from this 4,039, I need to find a factor of 4,039 that is also a factor of 4,039 squared plus 3. Okay, if it's a factor of 4,039, it's going to be a factor of 4,039 squared. What numbers could be a factor of 4,039 squared and also a factor of the denominator? The only possible numbers there are going to be factors of 3, right? In other words, if something's going to go into 4,039, it's also going to go into 4,039 squared. And if it also goes into 4,039 squared plus 3, then I've got some number that's going into 4,039 squared and 4,039 squared plus 3, which means that that number can't be any larger than 3. And in fact, it has to be a factor of 3. 3 only has 2 factors, 1 in itself. I'm not going to divide by 1 because that doesn't do anything for me. Can I divide by 3? A quick check of 4,039 shows you that the digits add up to 16 and it is not divisible by 3. What that tells us then is that I can cancel this 2 out of the numerator, but I can't cancel anything from the 4,039. Ultimately, our final answer is that the numerator of this thing is going to be 4,039. That's how it's done.
Hi, everybody. This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.